Welcome to my assignment video for the Avionic Devices seminar. In this one, we'll learn about some theory of lithium-ion battery packs and we'll make our own battery. So let's get started. This video focuses on micromobility. What kind of vehicle is that? Let's classify. We'll start with the least electrified vehicle class, the micro-hybrid electric vehicle. This kind uses a low-voltage energy storage system for high-power functions like electric power-assisted steering, not running the internal combustion engine for extended periods of time, some vehicle propulsion, and kinetic energy recapturing. The energy storage system is high power, high cycle life, low energy, and not thermally managed. It can be implemented by utilizing a lead-acid car battery, a lithium-ion battery, or by supercapacitors. Next is the hybrid electric vehicle. This class has higher energy demands, so a high-voltage energy storage system in the range of 200 to 450 volts is employed. A hybrid can propel itself electrically for moderate distances. Some thermal management can be achieved through usage. When the battery is too hot, the internal combustion engine takes over. This also reduces the requirement for a high cycle life. A hybrid electric vehicle that can be plugged in to charge its battery is called a plug-in hybrid electric vehicle. It requires an energy storage system capable of handling more energy. For a larger battery, a thermal management system becomes justifiable. The extended range electric vehicle provides all its motive power by using an electric motor, but there is a small internal combustion engine to provide additional power. When we think of a proper electric car, we think of the all-electric battery electric vehicle. These vehicles require significantly more energy and power from their energy storage systems than any other class of electric vehicle. The greater energy storage capability reduces the required number of charge cycles and thermal management becomes typical. The definition of the electrically power-assisted cycle varies depending on local jurisdiction. A bicycle with an electric motor that does only support and not replace the rider's power output is common among most definitions. The battery is low voltage and usually not thermally managed. Now, at last, the personal light electric vehicle. This group consists of very small electric vehicles and, depending on who you ask, either include or exclude the group of e-packs just mentioned. One definition requires the absence of a seat, so bikes are out. Another definition includes all personal vehicles with a mass less than 100 kilograms, so most bikes are in. The battery is not thermally managed either, and its construction is similar to an e-bike battery. The definition of micromobility, which this video is about, evades the conflict. Both e-packs and PLEVs are included. Just for the sake of completeness, the ICEV is the good old internal combustion engine vehicle. Batteries are made of cells. When I'm talking about a battery, I'm talking about the ready-to-use energy storage device. It consists of one or more cells. And I'm being lenient here. The Cambridge Dictionary actually requires a battery to contain at least 2 cells. I don't. There are a handful of cell chemistries to choose from when making a battery. 6 of the classic lead-acid cells are found in an internal combustion engine vehicle's battery. The use of nickel-cadmium cells has been heavily restricted in the European Union. Nickel metal hydride cells remain as a budget alternative to lithium-ion cells. And this brings us to the lithium-based cells. They far surpass other chemistries in energy density by both weight and volume. Lithium-ion was the preferred form of energy storage for electrified passenger vehicles in 2016. However, there's currently a trend towards LFP. Both the LFP and LTO chemistries are not as energy dense as lithium-ion, but they offer advantages in safety and cycle life. These are used when energy density is not the highest priority. That can be the case in renewable energy storage, forklifts, and autonomous mobile robots. However, Vehicles of the micromobility segment completely bank on the lithium-ion chemistries, so we'll focus on those. The nominal voltage is normally chosen to be an average voltage, so that it can be used to calculate the energy stored in a cell or battery. For typical lithium-ion cells, the nominal voltage ranges between 3.6 and 3.8 volts. The nominal capacity measures the electrical charge stored in a cell when discharged under certain conditions. These conditions are usually documented by the cell manufacturer in the datasheet. The capacity depends on the discharge current, the cut-off voltage, and the temperature. The unit is amp-hours. The energy of a cell is the area under its discharge curve. The discharge curve tracks the voltage while a cell is being discharged at a constant current. This makes the capacity axis equivalent to a time axis. The energy can be calculated more quickly by multiplying the nominal voltage with the nominal capacity. The unit is watt-hours. Even though current is normally measured in amps when talking about batteries, you'll commonly find the unit C. 1 C means the nominal capacity divided by hours. So for example, if a high current 5 amp-hour cell can deliver 1 C of current, it can deliver 5 amps. Lithium-ion cells can be connected both in parallel and in series to form a battery. When connected in series, the voltages add up. When connected in parallel, the capacity and current delivery capability increases. There is a shorthand for describing a battery configuration, NSMP. The number N before S counts the number of cells in series. The next number in front of the P gives the number of cells in parallel. Non-rectangular battery configurations don't really make sense, so these 2 dimensions are sufficient to describe a battery assembled from cells. A lithium-ion cell can be discharged until it reaches the cut-off voltage of 3.0 volts. Discharging to 2.5 volts is often possible according to the cell datasheet, and manufacturers gladly do so to inflate their capacity ratings. However, doing so will decrease the cycle life of the cell significantly. A simple and the most common charging method for lithium-ion batteries is the CC-CV method, or constant current, constant voltage method. A suitable power supply called a charger is required. The charger has a voltage and a current rating. It works in 2 stages. When the battery is in a low state of charge, constant current is applied to the battery. When the correspondent voltage reaches the fully charged voltage, it is kept constant. The current then slowly decreases. Once a time limit or the threshold of minimum charging current is reached, charge should be completely terminated. This charge termination current is specified in the cell datasheet. The cell is now fully charged. That means the anode has intercalated the maximum permitted quantity of lithium. When you go by the definition of anode and cathode, they should actually swap during the charging compared to discharging. But by convention the names stay, and the discharge process defines the names. Charging at high rates or at low temperatures may cause lithium plating and dendrite growth. Lithium plating degrades the battery, and dendrite growth may cause an internal short circuit. This may lead to thermal runaway and fire. Note that a lithium-ion cell can absolutely not be charged below freezing, that is 0 degrees Celsius. If the application requires such a capability, you may want to look into a different cell chemistry or employ thermal management. Both charging above the maximum voltage and discharging below the minimum voltage will cause chemical decomposition of the battery cell. Not only the chemistry, but also its physical format defines the cell. There are 3 main cell formats: prismatic, polymer pouch, and cylindrical. The prismatic cell is a rectangular cell with a hard aluminum or steel housing. It's manufactured either by winding or by stacking the jelly roll. That's the chemically active part of the cell. The form factor has the benefit of low internal resistance and high heat rejection, but suffers from poor energy density at cell level, both in volume and in weight. The polymer pouch cell is like a prismatic cell, but there is no hard exterior housing. It's made from a stacked jelly roll. This form factor offers highest packing density because there is no electrically inactive case, and also the highest design flexibility because it can be manufactured to fit any cuboid space. Drawbacks are the somewhat poor heat transfer and susceptibility to punctures. The cylindrical cell is both Tesla's and the Micromobility's form factor of choice. A jelly roll wound around a mandrel is inserted into a can made from aluminium. The can is then crimped shut. This is the most common format, with 8.5 billion cells manufactured in 2019. The cylindrical cell impresses with the lowest cost and highest degree of automation in its production. It is fully mechanically contained, which makes it easy to integrate into a battery. Unfortunately, the cylindrical shape limits packing density. Electrical paths are long, increasing internal resistance, and the center of the jelly roll has bad heat rejection. Example of the shelf dimensions are 18 by 65 or 21 by 70 mm. Both are used in electric micromobility, with a trend towards the larger size, partially caused by battery electric vehicles. Since cylindrical cells are so popular, let's have a closer look at them now. On the left side, we can see a couple of Molicel ICR 18650 cells, and on the right side, we cut one in half. On top, there is the positive pole. The negative pole is the whole cell can. For safer handling, the can is wrapped in purple isolating heat shrink tubing. The blue ring is an insulator, and there is another one at the bottom of the cell, not visible here. Above the insulator lies the conductive current collector, which is electrically connected to the cathode and the positive pole. The anode would be connected to the cell can at the bottom of the cell, forming the negative pole. There is a rubber gasket sealing in the cell can, which was crimped shut. The heart of the cell is the jelly roll. Remember that figure? The jelly roll is arranged in a symmetrically repeating pattern here. The separator sheet is the widest. Then, to the right of it, there is some electrolyte, a copper anode, again some electrolyte, another separator, electrolyte, and an aluminium cathode. The separator is ionically conductive, allowing the passing of lithium ions, yet electrically insulating, so the electrons have to travel outside of the battery. It's made from polyethylene, polypropylene, or a combination thereof. In the center of the jelly roll is a small steel tube called the mandrel. Other names are center pin or winding core, but unlike that name suggests, the mandrel is usually inserted after the jelly roll has been rolled up. One purpose of the mandrel is to apply pressure on the jelly roll from the inside to aid in its mechanical stability. A secondary purpose is to act as a conduit for gas in case of a cell failure. Through the mandrel, gas can escape towards the cell's vent at the top instead of rupturing the bottom of the cell can. This leads us to the safety chapter. Thermal runaway occurs when the temperature inside a cell exceeds a certain threshold. In such a condition, exothermic decomposition reactions inside the cell are triggered. Runaway means the reaction cannot be stopped once it has started. Triggers for thermal runaway are either manufacturing defects like internal short circuits or abuse, which is operation outside of a cell's specification. There are mechanical, electrical, and thermal types of abuses. The effects of thermal runaway are the venting of flammable gases which may ignite, and the emission of heat which may trigger thermal runaway in nearby cells, causing a thermal runaway cascade in the whole battery. At this point, we've learned enough to start making our own battery. This battery is supposed to go into an electric scooter, which needs 36 volts and less than 25 amps to operate. So I've decided for 40 Samsung INR 21750E cells to go in a 10S 4P configuration. Inspired by the way delicate eggs are transported safely within an egg carton, I designed and 3D printed my own safe containers for lithium-ion cells. The white cell holders consist of a bottom and the top part printed from PETG plastic, which are then glued together with superglue to form a single part with no unprintable overhangs. A pair of white cell holders hold 8 cells each. A black part snugs around the cells for extra stiffening. Now one segment is put together. 4 more to go. While I'm assembling, let's learn more about the safety at the cell level. The cell's current interrupt device, in short CID, is located in the cell cap. It decreases thermal runaway risk by electrically isolating the cell from the outside when the internal pressure rises above the activation pressure. This action will permanently disable a cell. The cell displayed has a spot weld that will fail at the activation pressure, causing the burst disc to bulge outwards, disconnecting the positive terminal of the cell. The vent acts like a pressure relief valve. Pressure is relieved in a controlled way through the intentional weak spot in the cell's cap. In the cell shown here, it is implemented as a burst disc. When activation happens, the cell vents. That way, rupture of the cylinder can be prevented. As the CID would have activated earlier at even lower pressure, the cell would be unusable after this event as well. A PTC, short for positive temperature coefficient, is an electrical conductor which experiences a resistance increase as temperature rises. It's placed in series with the cell into its cap and reduces current flow at high temperature. In this picture, it's the dark ring between the positive terminal and the burst disc. Tripping the PTC permanently changes its internal resistance by up to a factor of 2. The cell loses efficiency and emits more heat from that point in time onwards, up to 3.5 watts, so an overcurrent or short circuit event on the cell should be avoided for its whole lifetime. The separator itself can be a safety device too. A so-called shutdown separator partially melts at high temperatures and blocks its pores. This prevents any further ion transport through the separator, deactivating the cell. The cells need to be interconnected, but they cannot be soldered without damaging them. As we've learned, when the separator heats up too much, it could deactivate the overheated part of the cell. The datasheet also forbids soldering. Instead, to connect, nickel strips are spot welded to the cells. Here I made a couple of contraptions to cut and bend my roll of nickel into strips that will fit nicely in the bottom and the top grooves of my white plastic cell holders. The nickel strips must be chosen to have a sufficient cross-sectional area so they don't heat up significantly from the current they have to pass. Going beyond that, internal resistance of the battery decreases, so efficiency goes up. Obviously, there will be a point where material effort doesn't pay off anymore. I've decided for 8 mm thick and 0.2 mm wide nickel strips. By the way, in the Tesla Model S battery, the cells are interconnected using wire bonding. These thin aluminium bond wires act as fuses, allowing Tesla to emit both the CID and the PTC in their cell cans. During welding, I actually regretted my choice of 0.2 mm thick nickel strips. They were very hard to weld as my welder was not powerful enough. A good spot weld would not discolor the surrounding nickel. Discoloration is an indicator that the heat is being wicked away. The weld heats up too slowly and does not actually melt the nickel properly. I did improve my welding skills in later battery projects though. While I'm busy doing more than 500 spot welds, let's learn some more about safety. As we've seen, the cell has quite some protection against incorrect usage, but that may not be sufficient in some cases. This leads us to the most critical safety device, but it's not in the cell. The Battery Management System, or in short BMS, has the purpose to enforce the operational limits on the battery. This way, we can keep the cells within their safe operating envelope discussed earlier. To be precise, the BMS protects against overcharging, over-discharging, short-circuiting, and usage during extreme temperatures, and optionally other failure modes. Some BMSs have even more functionality, like monitoring the battery, estimating the state of charge, the state of health, and balancing the battery. Why is a BMS necessary? Didn't the cells already have safety devices? In multi-cell battery designs, the CID cannot be relied upon in some overcharge situations. It may fail to open completely. Additionally, above 50 volts, the CID may fail by arcing. A 12S PLEV battery reaches such voltage when fully charged. Similarly, the PTC has a breakdown voltage beyond which it becomes conductive. This voltage is not normally specified in a datasheet. Even the shutdown separator may fail at voltages of 20 volts or more, being only designed for low-voltage consumer devices. An overcharging cell would consequently overheat and enter thermal runaway. So one purpose is to ensure safety. Unlike other cell chemistries, lithium-ion batteries require a BMS for safe operation. Another purpose of the BMS is ensuring longevity. Especially in automotive applications, a lifetime of up to 15 years is expected. A BMS can enforce temperature-dependent operational limits, which is a major factor determining the lifetime of batteries. To enforce the current envelope, the BMS must monitor the complete battery current. This is often done on the negative pole of the battery. The BMS must also monitor the voltage of every single cell. To do this, a wire connection between every group of parallel cells is sufficient. Parallel cells are directly connected to each other, so they share the same voltage at all times. When any cell discharges below 3.0 volts, the BMS must terminate the discharge by shutting off the discharge port. Additionally, when any cell goes below 2.5 volts, the BMS must cut off all ports permanently. Safe operation can no longer be guaranteed after such an event. If any cell reaches 4.2 volts, the charge port must be shut off to terminate the charge. Note that the BMS cannot control the charge current, that's on the charger. It will just enforce the charging current limit by disconnecting the battery if it has to. Another duty of the BMS is to measure the battery temperature. Charging below freezing is forbidden, and so is discharging above around 60 degrees Celsius. Some cell manufacturers specify the current envelope of the cells in a temperature-dependent and even state-of-charge-dependent way. In that case, the BMS may need an internal lookup table. Fast charging generally requires warm but not hot cells. A BMS for a battery electric vehicle has the duty to request heating or cooling for the battery. Personal light electric vehicles are usually not thermally managed, just monitored, and often cannot fast charge. Last but not least, a BMS may be able to communicate to the external system through a data line. This gives the BMS the ability to announce the end of charge or discharge before enforcing it, or tell the current envelope or other parameters to the rest of the system. I'm finally done soldering. These are all 5 modules. Remember, this battery is 10S4P. To make it fit into the belly of the scooter, I basically folded it in the middle, so it's now 2 layers of 5S4P. The battery wraps around at its left end. To make this battery mechanically safe and stable, I inserted 2 threaded rods, which run for the entire length of the battery through all of the modules. 4 extra thin nuts go on both ends of both rods. I start by putting on this blue plastic cover. Remember, I already put on the cover on the other end of the battery last time. Now it's time to tighten the nuts. On this side I use a wrench, on the other side, with my other arm, I hold the rod with a slotted screwdriver. That's the purpose of the slots I carved into the ends of both rods. A large manufacturer of electric bicycle batteries had a very similar idea. The long Bosch power tube battery is being held together by bicycle spokes, whereas my battery contains 2 long threaded rods. Now I can establish the serial connections. Even though I could spot weld these as well, I decided to solder them. Soldering is possible in this case because the solder joints are pretty far away from the cells, so it won't heat up that much. Now I'm soldering a thick wire segment to the overall negative pole of the battery. The overall positive pole is already completed. The blue holder is designed so my BMS just slides in. This BMS can disable the battery by switching the negative pole. I must solder the corresponding cable of the BMS to the negative pole of the battery for this reason. The positive pole of the battery does not go through the BMS. Switching only one pole is sufficient to break the circuit. The BMS I'm installing actually features a data line. This particular BMS allows you to see all cell voltages and the number of total cycles of the battery using an Android app, among other things. I haven't yet explained what balancing the battery means. It means maintaining the cells at the same state of charge. While in an ideal world, a perfectly symmetrically built battery with identical cells will have every single cell charged and discharged in the same way. In practice, cells have tiny variations in capacity and self-discharge rate. Their SOCs and voltages may drift apart over time. The cell with the least charge will be empty first, causing the BMS to stop the discharge prematurely. The cell with the most charge, on the other hand, will cause the BMS to stop the charge before all cells are fully charged. Remember that cells connected in parallel will always be balanced because they share the same voltage. Only cells connected in series may drift apart and require balancing. There are two main methods of balancing: active and passive balancing. The difference lies in what happens with the energy. Active balancing moves excess energy from high SOC cells to low SOC cells. No energy is wasted, but the circuitry to achieve this is more expensive. The benefits of active balancing currently do not outweigh the cost. Passive balancing destroys the excess energy from high SOC cells. Every cell will be brought down to the cell with the lowest SOC. A simple passive balancing strategy that I've seen in a BMS for a PLEV is the following. Discharge any cell resting above 4.18 volts down to 4.18 volts through a little resistor. This operates completely independent of all the other BMS functionality. An imbalance of 0.02 volts can be resolved on every charge event using this strategy, but a very small fraction of energy is destroyed after every charge. The BMS will assume that the battery is constructed in such a way that all cells are identical and share the current equally. This can be achieved by wiring the cells in a symmetric way and using only cells from the same manufacturing batch. My BMS is a single module, so it has a centralized topology. This is typical for a relatively small lithium-ion battery like the scooter battery I'm building. For very large batteries, like the ones used in automotive applications, the BMS may be distributed into master and slave printed circuit boards. Time to solder the balancing wires. There are 11 of them on this BMS. Aside from balancing, the balance wires are also used to sample the voltage of every single cell in this battery. Finally, I secure the balance wires with some more Kapton tape. Cover the battery with abrasion-resistant paper and heat shrink everything in a big blue PVC coat. For later battery projects I actually changed my process. To avoid these manual, labor-intensive steps, I designed and printed plastic cases for my batteries. That's it. Ta-da! The battery is complete and can now be put in the footboard of an electric scooter. In case you wondered, with this battery I was able to achieve a real-world range of 45 kilometers with a Xiaomi M365 Pro scooter. This coincided with the range the manufacturer promised but did not deliver. I hope you liked this presentation and maybe even learned something new. Anyways, thanks for watching until the end and have a good one.